In this video, we're going to find the surface of an area of a cone of height equaling its radius, and we'll call that h. We're going to do that using two different approaches. We're going to do that using parameterization, and we're going to do that using the surface area formula where you have an equation for the graph, or where the surface is given by the graph of an equation over a certain region. So let's start with the parameterization. Let's start by thinking about what's this cone going to look like. The fact that the height equals the radius equals h is going to make life rather easy for us, because if we draw this cone, then we'll have a cone like this, and this value h, will also equal this value h. And I did not draw it that way, but you can pretend that it looks like that. What you will see if you are careful is that this is given by basically just looking at the cone, z squared equals x squared plus y squared, from 0 to z to h. So that will clearly give us a height of h, and if you think about what happens when you let z equal h, then at z equals h, you get h squared equals x squared plus y squared, and the radius of the base is h. So that does the job. That's all we really need to focus on. So let's start by parameterizing this thing. I know that I can parameterize the cone. Well, let's think what I want to do. I basically want to have a whole bunch of circles in my x and y coordinates. And I want so we'll have capital X of ST. I basically want a whole bunch of circles whose radius is given by the z coordinate. So what's that going to look like? Well, if I let S be the z coordinate, then my circles will be a radius of S cosine of t, then a radius of S sine of t. And then that does the job. That gets me these first two coordinates look like they'll give me a circle, and the radius of that circle is given by the z coordinate. So there's my parameterization. If I want to calculate the surface area, and I'm going to focus on the surface area of the sides first, that's going to be given by the double integral over my region D. It's not really a region, but it's fine. And then I'm going to take the cross product of the derivative with respect to S crossed with the derivative with respect to t. We should think about what that region is. That's basically saying, what are my S and my t going between? Well, I know my S, that's the z coordinate, that's going between 0 and h. And my t coordinate, I'm doing the full circle, that's going to be 0 to 2 pi. So I kind of know what this region D is going to look like. Now I want to find those partials. So t of s, if I take the derivative in respect to s, I'm going to get cosine of t, not theta. I'm going to get cosine of t, sine of t, 1. And if they take the derivative in respect to t, I'm going to get negative s sine of t, cosine of t, 0. So if I take the cross product of that, ijk, I didn't give myself quite enough room there. Let's go ahead and just write these things out first. So we'll have cosine of t, sine of t, 1. Then we'll have negative s of sine of t, cosine, or s cosine of t, right there. 0. If I take that cross product, well, in my I direction, I'm going to have 0 minus s cosine of t plus j. In the j direction, I'll have negative s sine of t minus 0. And in the k direction, I'm going to have s cosine squared of t plus s sine squared of t, because we have a negative and a negative making a positive there. So using some Pythagorean theorem and simplifying, we'll have negative s cosine of t, negative s sine of t, and s. So what's the norm of this thing? Well, the Pythagorean theorem is once again going to come in to save the day. That's going to equal the square root of s squared cosine squared of t plus s squared sine squared of t plus s squared, which equals, if you add that all up and use the Pythagorean theorem, that's going to be square root of 2 times s. Okay, so I found my magnitude or norm of TS cross TT, and now I'm ready to set up my integral. So, and I don't need much room for this, my integrand is going to be square root of 2s. My s values are going from 0 to h, and my t values are going from 0 to 2 pi. So that's going to be the integral from 0 to 2 pi of square root of 2s squared over 2, evaluated from 0 to h, dt, which equals the integral from 0 to 2 pi of square root of 2h squared over 2 from 0, dt. And since that's just a constant, I'm going to end up getting pi square root of 2h squared as the surface area of the sides of my cone. For the top, I'm going to be lazy and use that it's a circle of radius h. Could I parameterize that and do all this again? Sure. But you know what? It's a circle of radius h. So we're not going to do that. So that's just going to be pi h squared. And the total surface area is going to end up being pi h squared plus pi square root of 2h squared. And if you look at the formula for a surface area, that's not exactly what you get. But the good news is that if you let r equal h, it will be this. We're just looking at a very special case where the radius and the height are the same. And when that's the case, we get this nice formula here. Okay. Next, we're going to look at this using the other method where, you know what, I can describe this. So I described this earlier as z squared equals x squared plus y squared. I can write that as z equals the square root of x squared plus y squared. And when I can write this, my surface, and again, we're looking at the sides. When I can write my surface as a function of x and y, then I can use this special formula here, where I'm integrating over the region where this takes place over the curve. So I might ask myself, where is this region? What am I integrating over? Well, what I'm integrating over is the region, which is a circle of radius h in the xy plane. So my d is going to be a circle of radius h. Okay. So let's go ahead and see what we can do here. We can actually make very quick work of this depending on how lazy we want to be. So let's go ahead and see how that's going to go. So first I need to set up my integral. I need to find the partial of f. So we're letting f equal the square root of x squared plus y squared. The partial of f in respect to x, I'm going to take a shortcut here. Use the chain rule. Some stuff cancels out. It's lovely. You're going to get x over square root of x squared plus y squared. Same thing's going to happen if you take the partial in respect to y. So let's look at what this integral is. So I'm integrating d of the square root of f of x squared is going to be x squared over x squared plus y squared. Then we're going to have y squared over x squared plus y squared, and you might notice something very cool just happened, plus 1 dA. Once I actually simplify that, this is going to be x squared plus y squared over x squared plus y squared plus 1 dA. That's nice. That's just going to be square root of 2 dA. That's 1, we add them together, we get 2. And guess what? I'm integrating a constant function over a region whose area I know. This is just going to be square root of 2 times the area of D which equals pi h squared, square root of 2, just like we got earlier. Adding on the circle on top, we get the nice answer of pi r squared plus pi square root of 2 h squared. I should have made this an h. My apologies. Pi h squared plus pi square root of 2h squared, which is exactly what we got using the other method. So there we go. We just found the surface area of a cone whose height and radius are equal to each other using two different approaches here. So there you go.